Chapter 7 shifts gears a little bit, looking at air mass and synoptic climatology. In Part 1, we're just going to look at what air masses are, fronts, the boundary between air masses, what the typical distribution is around the United States, and also cyclogenesis, which is what helps mix these air masses together, causing fronts, causing lift, causing precipitation. The final part we'll look at here is what's called cutoff lows, is when a cyclone essentially cuts off from the jet stream, becomes a wobbly cylinder of cyclonic motion. And the reason I bring these up is they're actually important for explaining the anomalous precipitation events in the Boulder Front Range area. So synoptic climatology, the study of climates in relation to atmospheric circulations. It explores the relationships between the circulation, the preferential weather types you might get as a result, and the overall regional climate and the characteristics of that climate, including the extremes. A basic synoptic overview of Boulder, for instance, typically dry and warm whenever we have west winds because they're forced to come down the mountain, compressive and warm, lowering the relative humidity, giving us dry conditions. This is especially noticeable in the winter. Anytime it's warm in the winter, you'll typically have a strong west wind that's driving that compressional warming. On the other hand, whenever we have an east wind, an upslope storm, so to speak, if it has any moisture in it at all, it'll force that moisture to condense as it rises, expands, and cools, and you'll get cloudy conditions. So for Boulder, it's really important to understand the synoptic patterns that develop here to understand the climate that we live in. Air masses. An air mass is a large body of air with relatively uniform thermal and moisture characteristics. So it's a big chunk of air that has some signature amount of humidity, some signature temperature in it. How large is an air mass? Typically the size of Colorado or larger as far as area covered. The depth can vary from very shallow cold air masses that might be only 1 to 2 kilometers of depth to air masses that span the entire depth of the troposphere, so around 12 kilometers in height. The air mass names are described by their moisture and thermal characteristics. So you have two types of moisture characteristics, either a maritime, a very moist one that forms over water, has a lot of water vapor in it, or a continental air mass, which is very dry, typically forms over land, so it has less water vapor available to it. Thermal characteristics, there's 3 types primarily. The Arctic would be a very cold air mass, polar being a pretty cold air mass, and a tropical air mass being much warmer or even hot. Sometimes other books use equatorial air masses too to describe even warmer air masses. Air masses usually require both of these characteristics. So for instance, you can have a maritime tropical air mass, MT, which describes a warm, moist air mass, or a continental polar air mass that might, say, form over the Canadian plains. That would be cold and also dry. Here's where the distribution around the United States as far as the primary air masses are. Over here over Nova Scotia, certainly these Atlantic air masses are cold. Maritime polar air masses tend to form there, dive down over, say, New England. You also have maritime tropical air masses that develop off the Gulf Stream over the Caribbean in general. These can propagate and move into places like Georgia, giving them high humidity values. You can also have Gulf of Mexico air masses that are very warm, very moist, and they can infiltrate Texas, giving them the typical humidity characteristics they're known for, at least along the Texas coast. Down here along Baja, you have maritime tropical Pacific air masses infiltrating places like San Diego, Baja occasionally. Up here in the Pacific Northwest, anybody who lives in Oregon, Washington, or Northern California can tell you about the cool, moist air masses that are arriving off the Pacific there. And then here in the interior of the U.S., a lot of times we get inundated with continental polar air masses, a pretty cold, dry air mass coming down from Canada, or in worst case scenario, we might have one arriving all the way from the Arctic, an extremely cold air mass that's dry, coming into the U.S., giving us a cold air intrusion. The last one I'll note that actually is important for a number of weather-making processes are continental tropical air masses that form over the desert southwest or even in the Mexican deserts as well. And these definitely impact Boulder's climate and Colorado's climate in general. All right, so which air mass is the most dense? Well, whenever you're thinking about density, like in the oceans, you're thinking about the temperature of the air. So anything that's colder is going to be more dense. In this case, the Arctic continental air mass would be the most dense. So colder air is more dense than warm air. It also turns out that dry air is more dense than moist air. So the water vapor itself, H2O, weighs 18 grams per mole. That's relatively lightweight compared to N2 and O2, which are 28 and 32 grams per mole respectively. So anytime you have a lot of water vapor and air mass, it tends to displace the heavier species, N2 and O2. So the more water vapor you add to an air mass, it's going to lighten that air mass up. But in this case, the primary effect would be the temperature. So the Arctic continental air mass would be the most dense. Fronts. Fronts are the boundaries between different air masses. Typically, air masses don't come together and mix very well. Usually they have very different characteristics, different densities that force one air mass to lift up over the other one along what's called a front. Why do we care about fronts? Well, because they create weather. If an air mass is forced to lift up and over the other air mass, that means that air mass that's getting lifted is going to cool due to expansion and possibly reach its dew point, become saturated, and produce precipitation of one type or another. Fronts are classified based on the thermal and moisture characteristics of the air masses that are colliding, the direction of movement of the air masses while they collide, and whether the front's in contact with a surface or only are found aloft. This tool can show typical fronts and how they work. First one I'll show is a cold front, which is a cold mass of air digging underneath a warm mass of air. And where they collide at the surface is known as the cold front. Again, it's important that the cold air is advancing into and under the warm air mass. You can see that the area of lift and the resulting precipitation moves in time. Next, I'll show the warm front. Warm air, being less dense than cold air, has a harder time pushing that cold air. It does manage to push it, however, they typically go more slowly, these warm fronts, because the warm air doesn't have as much momentum. It's less dense. The other thing you can see here is that it tends to not have as sharp of a lift, so you tend to get more elongated or stratus type clouds over a larger horizontal distance. So you tend to get more flat clouds that could extend for 50, even 100 miles. Cold fronts have a sharp area of lift. They move very quickly. Warm fronts have a long, elongated area of lift, flatter clouds, and they move quite slowly. A stationary front is a boundary between a cold and a warm air mass where the actual boundary at the surface does not move over time. It's kind of stationary. This isn't drawn particularly well. However, you can get the warm air mass still gliding up and over the cold air mass, giving you an area of lift, even though the front itself at the surface is not moving over time. So this can produce a lifting mechanism that stays in place over time, and stationary fronts are therefore associated with floods because it continuously rains for a period of perhaps 3 or 4 days in one location. Now, occluded fronts are essentially where a cold air mass or a cold front, boundary between a cold and warm air mass, is moving fast and it actually catches up to an existing warm front. So that's called an occlusion when that happens. And they're going to show this here. The cold front's advancing to the right. The warm front's kind of stationary in here, moving quite slowly. The cold front caught up to the warm front. Both of them were attempting to lift the warm air mass over each type of front, and as a result, the occlusion does it even better. Now that warm air mass is really pushed up by the cold air mass from behind the cold front, and also the cooler air mass ahead of the warm front. So that warm air gets pinned aloft, and that's called an occluded front. We've seen in previous lectures that wherever you have cold air, it compresses all the pressure surfaces, making for relatively low pressure aloft. And in a warm air environment, the pressure surfaces get pushed upwards, making for higher pressure aloft. This means that warm and cold surface air can lead to a pressure gradient, specifically going from the warm air column towards the cold air column. And here, if the pressure gradient is going from the warm air towards the cold air, it's going to try to push the wind towards the north here, towards the cold. In the northern hemisphere, that'll turn, due to Coriolis effect, out of the page here, or out of the screen looking at you. So this forms a jet stream where that pressure gradient is strongest. And the real key here is that the surface temperature gradient is connected to the upper level pressure gradient and therefore winds. The jet exists due to this equator to pole temperature gradient overall. Its precise location, however, is above where cold and warm air masses meet, since they are what dominate that pressure gradient aloft and therefore the winds. The seasonality of the jet stream, it simply follows the greatest temperature gradient. It follows that temperature gradient north in summer. As the Arctic starts to warm up, the most extreme part of the cold is right at the North Pole, and so the temperature gradient's at a maximum farther north during summer. During winter, the maximum temperature gradient moves to the south, and with it the pressure gradient aloft and therefore the position of the jet stream. So you have the polar front jet stream average winter position here across the middle of the country, but then in the summertime it migrates well into the fringes of the United States and Canada, and it slows down as well. So why is the jet stream twice as strong, meaning twice as fast in the winter? Simply because that surface temperature gradient is larger in the winter. There's a bigger change in temperature between the subtropics and the pole during the winter time when the Arctic's really very cold during the winter. Therefore, that drives a really strong pressure gradient aloft, which drives a really strong jet stream during the winter time. Now, when we looked at geostrophic winds, it was a perfect balance between a pressure gradient force and a Coriolis force. So it turns out that a pure geostrophic balance would only happen in straight line winds following straight isobars. So again, geostrophic winds try to go from high to low pressure, but Coriolis turns them until there's a perfect balance between the pressure gradient force and the Coriolis force, and instead they end up going straight along isobars, or along lines of constant pressure. So when we looked at all the force balances, we looked only at pressure gradient force, Coriolis force, and friction force. It turns out you have to consider another force, the centrifugal force, for a curvature of a flow. So in this case, we have a low pressure system in the northern hemisphere. As a result, you're going to get cyclonic flow counterclockwise in the northern hemisphere around. And we always know that the pressure gradient force is going to go from high pressure towards the inside of the circle to low pressure. So that's drawn here as a vector or as a force pointing towards low pressure. If the flow is going around here, the tangential flow is around the circle here, then we know Coriolis force is always going to be in the northern hemisphere to the right of that flow, as shown. However, there is always a centrifugal force trying to throw this parcel of air off the merry-go-round, so to speak. So it's always directed outward, away from the axis of rotation. So you have this additional centrifugal force in a balance anytime you have curvature and a flow in the atmosphere. Now this would be upper atmosphere circulations because we're not considering friction, which becomes important near the surface. So in this case, around a low, you have the pressure gradient force going one direction, and then the Coriolis force and the centrifugal force balancing that pressure gradient force. So around a low, Coriolis force has the help of the centrifugal force to balance that pressure gradient force. The net result is that a force balance is achieved at wind speeds that are lower than geostrophic values. So anytime you have the winds turn cyclonic, or in this case going around a full cyclonic circle here, they're going to go a little bit slower than geostrophic wind speeds, which would be more appropriate if you're looking at straight line. Now around a high, everything changes because now you have the pressure gradient force going from high to low, trying to push outside the circle here. Coriolis force, if the flow is going clockwise in the northern hemisphere, Coriolis is always to the right and it's pointing inside towards the high pressure. And the centrifugal force is always trying to push you away from the axis of rotation, off the merry-go-round, so to speak. So in this case, the pressure gradient force and the centrifugal force are both acting against the Coriolis force. If you're at a given latitude, the only way to get the Coriolis force stronger is to make the wind move faster. So around a high, the Coriolis has to balance both the centrifugal and pressure gradient force. So the force balance is only achieved at wind speeds that are slightly higher than geostrophic values. So anytime wind turns around clockwise in the northern hemisphere, it goes a little bit faster than it would if it was going in a straight line. Anytime it turns counterclockwise, it goes a little bit slower than it would if it was going in a straight line. So that any time when the jet has curvature to it, there's difference in the speed of parts of that jet, and this can lead to the creation of high and low pressure at the surface in what's called a dynamic creation of high and low pressure at the surface. So let's look at this. We're looking at about 300 millibar level in the atmosphere, way up where airplanes fly, so very high in the atmosphere, above the level of where friction is an important effect. So let's look at the features here. Here's the pressure trough. That means an area of low pressure aloft, and typically for west to east winds, they are shown as kind of a low spot in this two-dimensional diagram. And so you can see a lower pressure here. Anywhere you went, the pressure would increase from there, so you're in a low spot of pressure there. Winds are forced to turn cyclonically or counterclockwise in the northern hemisphere around low pressure. So as it turns around low pressure, it must go slower than geostrophic winds would from the arguments I made last slide. As it goes over a high pressure ridge, and this is what a high pressure ridge looks like in the upper atmosphere again, relatively high pressure here, if you follow these isobars, you'd be greater than 305 millibars in this area, and anywhere you go in any direction, you'd be decreasing your pressure. So therefore, this is drawn as a higher pressure ridge. And winds are forced to go anticyclonic or clockwise in the northern hemisphere around that high pressure ridge. As a result, they go faster than geostrophic values. So add these up, anytime it turns clockwise, it goes faster than geostrophic. Anytime it turns counterclockwise in the northern hemisphere, slower than geostrophic. What this means is there's points in between the ridges and the troughs where air must be changing speeds. So if it has to go slower here but then speed up to get over the next ridge, there's an area here where the winds are speeding up. What this means is it's just like the start of a marathon, so to speak, where everybody's clustered together and then the starting gun goes off and they all spread out as they're increasing their speed. This means that the molecules are literally spreading out here or diverging, and that lowers the pressure underneath there at the surface, because if you remove molecules from an atmospheric column, there's less mass above you, there's less weight above you, and that defines your surface pressure. Less weight above you, less molecules means surface pressure is decreasing under areas of upper level divergence. At the same time, if this air must go fast over this ridge, slower around the next trough, it must be piling up or converging in this region. This would be kind of an example of a stoplight anywhere you are, where cars all of a sudden cluster together as they're forced to slow down. So there's a general pileup of molecules here, increasing the surface pressure underneath there. So what I've kind of put in here in the animation is the surface flow you'd expect underneath this value. So again, this is at jet stream level. The curvature in the jet stream dynamically removed molecules in this region, reduced surface pressure, and here's the flow you might generally see at the surface underneath this part of the jet stream, rotating cyclonically. At the same time, underneath an area of convergence, you'd have higher pressure, and you'd likely see anticyclonic motion. Here's a pretty good drawing showing that. Again, here's the axis of the trough right here, where it's deepest, the lowest point aloft, and here's the axis of the ridge. In between the ridge and the trough, you get that convergence zone where you're adding more molecules than you're removing, which increases surface pressure, giving you clockwise flow at the surface. Over here, you're between the trough and the following ridge, which isn't drawn quite well, but consider there's a ridge over this way, a trough here. In between, this is an area where the winds are forced to speed up, and as a result, you're diverging, you're removing molecules out of this column. So that lightens the weight of the column, lowers the surface pressure, and you're going to get cyclonic flow or counterclockwise in the northern hemisphere around that. Why we want to explain this is because there was a connection, right? There was a temperature gradient that formed a jet stream. Now the jet stream, anytime it has curvature to it, can spin up highs and lows at the surface, and it can really help mix that temperature gradient up. So again, in summary, the jet can force a low, and this is what's shown here, which forces air masses to mix and hence fronts. So what's shown down here is that because of the curvature in the jet stream, it causes a low pressure at the surface, which rotates cyclonically. That causes north air to move and meet up with warmer air to the south, shown as a cold front here. And it also causes southerly winds on the right side of the cyclone. So you're taking Gulf of Mexico moisture and then pushing it up towards cooler air that exists over the northeast, and that's shown as a warm front. So this is generally a weather maker. That jet stream can spin up highs and lows, which can create fronts, which create weather. But also it's important for general energy transport processes too. Now what's shown here are areas of cyclogenesis where these cyclones tend to form up. In other words, where the jet stream has enough curvature, enough kinks in it to produce that upper level divergence and the resulting surface low, which will give you what's called an extratropical cyclone. I just want to show in general where they form. I will say a couple things, that the jet stream tends to have kinks in it wherever you have differences in temperature, right? So you have differences in temperature often during certain seasons when you have an ocean which has high thermal inertia next to a land surface. So you can have kind of differences in temperature along coastlines here, the Hatteras low, the Gulf low. That can happen a lot during the winter where it's getting colder here, the water's still warm. Up here you can have temperature gradients along those water surfaces as well, along coastlines. And also there's an effect from mountains. So The Canadian Rockies are up in this region, and on the leeward side of those Rockies, you often get kinks in the jet stream that can help form low pressure at the surface. Same deal with our southern Rockies, we get Colorado lows. A lot of the country's lows are actually formed on the eastern plains of Colorado as a result of kinks in the jet stream formed by the mountains, which leads to upper level divergence in a certain zone in eastern Colorado, and then a low pressure at the surface, which starts to propagate over towards the Chicago area on average. You can immediately see that these areas that are well known for having tricky weather patterns, there's reasons, because a lot of the cyclones that develop end up propagating over them. So if you compare this pattern, this general pattern of where cyclones start and where they head, you can look at the distribution. This is the wintertime distribution of precipitation over the United States, and you can see it really relates well to the position of where those extratropical cyclones end up being, because they end up forming fronts, and they end up forming what's called frontal precipitation. You can flash back and say, wow, they really run over this area quite often during the wintertime, and that is true, and you can see their precipitation effects from the data. At the same time, you get in a lot of extreme low pressures entering the northwest part of the country as well, and that correlates with this Gulf of Alaska lows that form, and also there's certainly an orographic effect in this part of the world too, since there's mountains. And I just want to point out with this more elaborate network of cyclone tracks across the US that they do tend to traverse along New England quite a bit. Mount Washington Observatory in New Hampshire there, at the summit of Mount Washington at about 6,300 feet, we frequently had storms working up there as a weather observer. There was only one day in 2 years that I didn't see a cloud during my hourly observation. So quite frequent weather patterns happening across there, and as a result, they end up with a lot of ice, rime ice shown here, a lot of weather. For Colorado's concerns, I want to explain what a cutoff low is, because it is a dominant part of our big winter storms along the urban corridor. So what happens here, the dashed lines are showing the upper level flow, again a trough aloft here, and we can assume there's a ridge next to it. In between those two, you're going to get low pressure at the surface, and that's what I'm showing with these animated arrows, rotating cyclonically. It's going to drag cold air at the surface this direction, and then it's going to drag warm air at the surface to the north on the east side of the cyclone. What happens next is, because you're taking cold air and pushing it underneath the trough, that's what forms a trough in the first place. Low pressure aloft is formed by cold air underneath it. So if you push more cold air underneath it, it's going to depress that trough, make it deeper. At the same time, if you push more warm air underneath the existing ridge over here, that's going to amplify it, make that ridge higher. So there's a process where these cyclones kind of help make themselves stronger over time by amplifying the curvature in the jet stream, so to speak. Part C down here is showing that process still going on, and now you're just pushing a lot more cold air underneath the trough, getting even deeper and deeper and deeper. You can assume the ridge was getting a little higher and higher and higher. The dominant effect here is that you're starting to push so much cold air, you've almost wrapped at the surface. You're starting to get your occlusion. That means that cold air is starting to wrap around the cyclone at the surface on all sides. So what's the fate of the warm air? The fate of the warm air is to get pushed aloft because it's less dense than the cold air. So the cold air is now circling at the surface and really wrapping up the cyclone. And that's shown finally here in point D as an occlusion, where again, a cold front has wrapped around this whole thing, caught up to the slow-moving warm front, and now you're occluded. The interesting part of when this happens, since you wrapped cold air around the entire surface cyclone, now the upper level atmosphere responds by having a circle of low pressure kind of pulled out of the jet stream. And so now you have a low pressure that was formed at the surface dynamically by curvature in the jet stream, so it pulled molecules out of the upper atmosphere, lowered the pressure, but now you've additionally created low pressure aloft thermally by having a little circle of cold air at the surface, which depressed those pressure surfaces aloft. And this is what's called a cutoff low. So this is kind of a figure of what a cutoff low looks like. It really is cyclonic flow, or counterclockwise flow in the northern hemisphere at all levels. And that is not what a developing surface cyclone looks like. Here we can see a developing surface cyclone. It has surface winds spiraling cyclonically at the surface, but aloft, the winds are actually going from southwest to northeast. So there is no cyclonic motion aloft. When you cut off though, however, you do have cyclonic motion at all levels. Now these cutoff lows are no longer getting stronger. In fact, they'll weaken due to friction converging air at the bottom of them over time, but they can last for 5 to 7 days just due to the momentum they had when they spun up. Since the cutoff low is cut off from the jet stream, it no longer has that source of divergence to make it stronger, but also since it's cut off, it's no longer very predictable. They can wobble about, they can even go from east to west or west to east. They kind of move about, they're hard to predict where exactly they're going to go or for how long they're going to last. If a cutoff low parks itself to the south or southeast of the Front Range, shown here, it can create very deep upslope flow for many days. We have seen 2+ feet of snow in Denver from these types of storms and more than 8 feet west of town in places like Sugarloaf, Netherland, places that are really strongly affected by upslope type storms. Now again, the real distinction here is the fact that the winds would be from east to west up our mountains at all levels. That deep upslope component is important in making our biggest snowstorms. In fact, all of Denver's biggest snowstorms have involved a cutoff low to some degree or another. If you have a developing low again, sure, you could have upslope at the surface, but the winds aloft would be southwest to northeast, so definitely not upslope. Only cutoff lows can have upslope components, easterly winds against our mountains at all levels. In October 97, this happened, one of our bigger cutoff low storms. The cutoff low parked here. Here we're looking at the 500 millibar surface, showing low heights of that 500 millibar surface. So this is showing a cutoff low here, low pressure aloft, and there was low pressure at the surface here at this time too. This gave us 2 to 3 feet of snow in town in Denver and also 4 to 5 feet in the foothills. So the overwhelming majority of large Front Range precip events were caused by cutoff lows. And it's not just wintertime, it can also be the shoulder seasons, the spring and fall too. Summary from Part 1 of Chapter 7, air masses take on characteristics of their source region. Fronts are where these air masses are collide, and they're big weather makers. The jet stream forms above strong temperature gradients. The jet stream can dynamically create highs and lows, which force air masses to collide. So they help force these fronts, so the jet stream's associated with frontal precipitation for that reason. The jet stream also causes exchanges of heat and moisture, plus the weather from these fronts. The jet stream is an important driver of mid-latitude synoptic climate patterns as a result. Cutoff lows, finally, are a big player for Front Range anomalous precipitation events.